Well, every one of you is familiar with prime numbers. They are all the numbers greater than 1, mind it, which are not divisible by any other number other than 1 and the number itself. An interesting fact to notice is that 1 is not a prime number. Well, then, is it composite? No, it's neither. Well, by definition is not a answer to why mathematicians chose that 1 would not be a prime number. The answer to this lies in the fact that the utility of prime numbers depends on the fact of whether a composite number can be represented as a unique combination of the powers of prime numbers. For example, 8 is equal to 2 cubed, 15 is equal to 3 to the power 1 into 5 to the power 1. If 1 is considered a prime number, this whole concept and the utility of prime numbers becomes meaningless, since 1 to the power any number is 1, and all numbers are divisible by 1. So representation of any number as the unique products of prime's power will not be possible.
Now that we have known what a prime number is, let's get some insight about it. Prime number have always troubled the mathematicians, especially because of its non-representability. I mean that if you are given the first n consecutive prime numbers, you cannot represent the n plus 1th prime number using the previous primes. One way of representing a prime number "p" greater than all the previous n consecutive prime numbers "p1", "p2", "p3", "pn" is that we write "p" as the product of all the previous prime numbers plus 1. This "p" is greater than the "pn" and a prime, since if you divide it by any prime number, it gives the remainder 1. This does not imply that there are no primes between "p" and "pn". Let's understand this with an example. We consider 2, 3, 5 and 7 to be the n-prime numbers. So the product of all these prime numbers are 2 into 3 into 5 into 7 equals 210. Adding 1, we get 211, which is a prime number. But there are 11, 13 and 17 prime numbers between them. Another interesting problem with the prime numbers is the counting problem. How many primes are there in the first 10 natural numbers? Let an denote the number of primes in n consecutive integers. It was found that n by an follows a curve close to 1 by log n as n increases. So we can write that for large values of n, n by an divided by 1 by log n tends to 1. Therefore, an tends to n by log n. This is an approximate value, but you will be amazed to know that we can exactly count the number of primes in a range. Or we can count only if the Riemann hypothesis is true. To know this, we must first understand the Riemann's zeta function. Riemann's zeta function looks like this, but can also be written as the product of all prime numbers in the following fashion. The zeta function converges for all s greater than 1. Now Riemann found that the symmetry line of the zeta function is s equals to half. Thus, it becomes deterministic for s less than 0. Thus, the uncertain zone remains in 0 to 1. Riemann gave a hypothesis that all the zeros of the zeta function in 0 to 1 lies in s equals half. It has been tested for a huge range of number, but not yet proved. This is actually a millennium problem, and one could get $1 million prize money if he or she can solve it. That is, disprove or prove it. And if one can prove this, then one can calculate the number of primes in a given range. Another interesting conjecture is the Goldbach conjecture. He claimed that every even integer greater than 2 can be represented as the sum of two prime numbers. For example, 4 can be represented as 2 plus 2, 6 can be represented as 3 plus 3, 8 can be represented as 5 plus 3. Well, you can try as many numbers as you want. It holds, but hasn't been proven yet. The basic problem with this problem is that the primes are related to multiplication, and this problem is related to addition. There are many more weird stuffs about primes, but we end here. Thanks for watching.